Okay, in which case I think it's 3:30 UK time, so make a start now. So welcome to everybody to this webinar. I'm Andy Brown, Director of Research at ECMWF. I hope everybody's keeping well in these difficult times. And it's a real pleasure that we're still managing to progress our science and to be able to sort of tell you what we've been up to and the science in the forthcoming cycle 47R1. And we're really delighted to still be able to go ahead with that in June. I hope my Wi-Fi is up to this. I have two children in other parts of the house competing with me doing online school lessons, so hopefully we'll be all right. And plan at the end of the session to take questions through the chat. If people just type in questions when as they have them, and then I'll try and take those questions at the end. So no further ado, I'll get going. I was thinking just a year ago now, I was doing similar webinars on a very successful cycle 46R1, and it makes it very tempting to think that sort of ECMWF progress in the forecast systems is all about the cycles. So I just wanted to very quickly just touch on some of the other improvements that have come through the year, because we're making changes to the observation usage all through the year, and that contributes very significantly to the improving scores between the cycles. So just in the last year, for example, we've implemented the remaining METOP-C instruments, the atmospheric motion vectors from GOES 17, radio occultation, COMPSAT-5 data, that's our first use of Korean data, just recently implemented the COSMIC-2 data, and also the microwave humidity sounder on the Chinese FY3D. And maybe sort of most high profile of all, back in January, we started operationally assimilating Aeolus data. So that's the first Doppler wind LiDAR in space, so the first direct wind measurements from space. And we've seen got very major improvements through the use of that data. So with that preamble, I'll now move on to sort of the next exciting upgrade, 47R1. So I'm going to first run through the data assimilation and observation components, and then we'll go through the model. So on these, the first four of these, I'm going to show a couple of slide examples or more details on each of them. So I won't touch on those now, just to very briefly mention the other ones. The revised ATMS observation errors. Back at the last cycle, we introduced interchannel error correlations for the Suomi NPP instrument. And this is really doing the same thing for NOAA 20, the ATMS on NOAA 20. The channel-specific aerosol rejections is if there's too much aerosol in the atmosphere, we currently reject all the infrared spectrum because of the aerosol contamination. What we're doing here is a rather more subtle rejection where the low peaking channels, which are directly impacted by the aerosol, get rejected, but we would still keep using the higher peaking channels. So it lets us keep using more of the data that's got useful information and extract more information from the IR sounders. And the last change is a detailed change to the vertical interpolation in the refractivity and the GPSRO analysis. So moving on to the other items that I was going to show in more detail. The first of them is developments, I think really quite exciting developments to the weak-constraint 4D-VAR. So just to show schematically, for and you're not familiar with this, what the weak-constraint 4D-VAR is doing. On the left, we have a schematic of what happens in the assimilation window when we have strong constraint 4D-VAR. So you start with a first guess trajectory across the assimilation window, the blue line, and then we get various observations in from different sources, and then using assumed errors in the background trajectory and assumed errors in the observations, you then come up with the, if you like, the compromise fit, the analysis. If we go to weak constraint 4D-VAR, it's the same, but additionally, there's an extra term allowing for systematic errors in the model. So schematically, you can see the red line is now jumping down every now and again through the assimilation window. So we're also allowing in the assimilation for errors in the model. And what we've done is a major development to how we do that. One of the challenges, we've been doing this for many years in the stratosphere, but one of the challenges has always been that the model error term and the background term have been rather competing with each other. And so it's been difficult to get the full value out of it. But we did some work looking at the model errors. So the plot on the right shows stratospheric temperatures, the difference, a long average, the difference between the short-range forecasts and the GPSRO data. And you can see that the patterns of model error are really quite large scale. This isn't sort of small scale features, it's very large scale. And the new version of the weak-constraint 4D VAR is better representing these very large scales of the error. So we've got the new formulation to get these covariances with the longer length scales. And if we look at what that does, if we just look at the plot on errors relative to radiosonde data, so we have mean temperature errors on the horizontal axis, pressure in the vertical from the surface up into the stratosphere. If we just concentrate on the solid lines, the solid red line is if we use strong constraint 4D VAR, so no model error term, the difference between the observations and the background. So the error in our short range forecast. And you can see we have a warm bias of perhaps 0.6 degrees in the stratosphere. If you then look at the green line, that's what our current weak constraint 4D VAR takes us to. So if you're optimistic, it's slightly pulling in the right direction. The errors aren't quite as large, but most of the error remains. The new formulation is shown in black, and I think you can see we've very significantly pulled the analysis back towards the observations. So I think a major improvement, if you look higher up, the upper stratosphere where our initial bias is in the opposite direction, again, we get the same effect. It's pulling us the right way. So a major development there to the weak constraint 4D VAR. I think we've struggled for years to get as much value out of it as we hope to. So that's a value for our forecast system, and will also be very valuable for the future reanalysis. On a different subject, looking at how we use satellite data. So, of course, lots of the satellite channels are sensitive to the surface and the skin temperature at the surface. Until now, we have to associate an error. How uncertain are we with our sort of first guess of the surface skin temperature? And we've used a rather crude formulation, just assuming it's a uniform 5 Kelvin over land. And the innovation here is swapping to, we run this ensemble of data assimilations every cycle. So you get lots of different answers. You can see how variable they are. So we're now assessing the background errors from skin temperature. How uncertain are we about the skin temperature from information from that ensemble of data assimilations? And the result of that is you end up with a spatially and temporally varying error. So if you look, for example, at the top panel, that's IASI on METOP B. So that's a morning orbit, 9:30, a 9:30 orbit. And you can see a different pattern, the warmer colours, the bigger errors, for example, over the Sahara or different parts of the globe according to vegetation. And if you look at HRES, the NOAA 20, on NOAA 20, you see a similar geographic pattern, but slightly warmer colours. And that's consistent with the fact that HRES has the 1330 orbit. And so by day, with more solar insolation, there's more variability in the surface skin temperature. And so this use of the EDA is correctly getting us a physically realistic uncertainty. We can then better use the satellite data. A separate issue is in the 4D VAR, we have the inner loops and the outer loops as we converge towards the analysis. And at the moment, the inner loop minimization time step is double that used in the outer loops. So we're using a 900-second time step in the inner loop and a 450-second in the outer loop. And that introduces a different propagation speed for gravity waves in the inner versus outer loop integrations. And in the stratosphere, that can result in some spurious features. You get gravity wave-like features set up in the increments that the data assimilation gives that are spurious. If you look at the top right panel, that's the temperature increments in the stratosphere. And you can see both around Antarctica and also in a band from Greenland across into Europe, we've got some very sort of wave-like signals of temperature increments being introduced. And those are fully spurious, because if all we do is change the inner loop minimization time step for 450 seconds, the plot on the same scale looks like the plot below. And so that's clearly, it's not a good thing to put spurious gravity waves into the analysis. And if we do that, we clearly see better stratospheric analyses and forecasts. But perhaps more interestingly, we can see benefits right down to the surface. If we look at the fit of surface pressure or near surface winds to observations in the analysis, just by changing the time step, we get a better fit to the data. And if we look at the bottom panel, that's showing in the forecasts the absolute surface pressure tendency. So in a sense, a measure of how balanced is the analysis. And you can see before this change, the red and black lines, the first few hours of the analysis, we've got really quite large increments in the forecast, or tendencies in the forecast that fall away. And with this change, we move to the green line. And so it's a much more balanced analysis. So changes to the data assimilation, biggest impacts in the stratosphere, but a measurable impact on improving the tropospheric forecast, surface pressure in particular. I think the last aspect I was going to highlight from data assimilation and observation side was changes to how, it's effectively how we cycle the forecast through the day. If you look at the bottom left panel, this is just trying to show schematically, try to move the cursor and changing the slide. If we look at the bottom left panel, this is showing schematically how our forecasts currently run. So coming in from the left-hand side, we're about to start a new cycle of the forecast. So we come in with a background and a first guess from the previous forecast, and we do what we call the early delivery 4D VAR. So that's got an 8-hour window. We'll do the assimilation over 8 hours, 21Z to 5Z in this case, and that's the analysis from which we run the 10-day forecast that goes to our users around the world. Having done that, we then, when we've got more data in, we then redo the analysis. That's this 12-hour 4D VAR that we call the long window 4D VAR, to use all the observations we've now got in, and to use a longer assimilation window to get the best possible background and first guess that can then pass into the next cycle, the next early delivery forecast. So that's how we currently work. What we're moving to is what's shown in the right. So again, we come in with a background and first guess in exactly the same way. We do the early delivery 4D VAR, and we run the forecast from it. But now when we want to do the long window update, we still take the background from where we got it before, but that early delivery has already done an analysis. It's done lots of outer loops. It's taken into account lots of observations already. So it's already got a much better first guess than we had before. So by taking the first guess from there, we're giving the 12-hour 4D VAR an advantage. It's got a better starting point. It's implicitly done a number of outer loops already. And so that lets us do a more accurate analysis, which will then pass into the next forecast. And if we look at what that does, these plots are just showing against various different satellite data how well the background, the short-range forecast, fits to observations. And if the numbers are less than 100%, it's fitting better. So I think there's a statistically improved fit to almost all of these observations through doing this. So we're very confident we're getting a better analysis out of this change. I should acknowledge, in doing this, when we then verify our forecasts against our own analysis, particularly in the tropics, you do see an apparent degradation. And that's an issue with a change of the characteristics of the analysis, not the quality of the forecast. Because if we verify either against an independent analysis, like ERA 5 or a different centres analysis, or against observations, we don't see that degradation. Okay, so changing topic onto the model. As ever in this cycle, there's innovations from the observations and data assimilation side, and another lot of innovations from the model side that all come together. So I'm going to sort of run through these in turn, so I won't read them out at this point. The first one I wanted to highlight is Quintic vertical interpolation in the semi-Lagrangian advection scheme. Talk around the top panel here, panel A, to give the motivation for what we're doing here. So this is looking, so a cross section, so North Pole to South Pole along the x-axis, and surface up to the upper stratosphere on the y-axis. And this is looking at the mean temperature change if we go from a low resolution TL255 model to the TCO1279 model, that's the 9 kilometers that our high-res system uses. And what you can see is we've actually got a rather unpleasant resolution sensitivity there, solely by changing the horizontal resolution. In the stratosphere, above about 100 hectopascals, we're getting a cooling of somewhere between half and order 1 degree cooling, solely by changing the horizontal resolution. And the reason that's happening is when we go to higher horizontal resolution, the model starts resolving more and more gravity waves, which are real features of the atmosphere, but it can't handle them very well because it doesn't have sufficient vertical resolution. Once it starts getting the more gravity waves from the higher horizontal resolution, the vertical resolution isn't keeping up. And so you get this effect of a cooling in the stratosphere. And one way we can solve that is by just throwing lots more resolution at the problem. If we go, instead of the 137 levels that we use, to 200 levels, this problem largely goes away. But that's a rather expensive way to solve the problem. When we get enhanced computer resources, we'd rather not, if we don't have to, put lots of extra resolution in the stratosphere when there's other things where we could improve the forecasts more with that extra computing power. So what this is doing is changing the accuracy of the numerical scheme. So we have to do an interpolation to get departure point values of temperature and moisture. And at the moment, we use a cubic scheme. And what we're going to change to here is using a Quintic, a 5th order scheme, instead of a 3rd order scheme. If you look at panel B, that shows the impact at low resolution of changing from the cubic to the Quintic. And it doesn't make that much difference. It's not zero, but there's not very big effects. And that's because at these low resolutions, we don't particularly have these gravity waves that cause a problem. So it doesn't particularly matter which interpolation scheme you use. If you look in panel C, that's showing what happens at 9 kilometer resolution, the high res resolution, when you change from Quintic to cubic. And you see you get a systematic warming through the stratosphere, which is almost exactly in antiphase with the problem we had in panel A. So really very largely reduces this problem. So that's very good immediately for the stratosphere in this cycle. But this whole area of work is also very important for our future strategy for where we go with our systems, because we're planning with enhanced supercomputer coming in Bologna and the cycles beyond that. Where do we go? And this is showing that 137 levels gives us sufficient resolution in the vertical. We don't need to invest more in the vertical, at least for the horizontal resolutions we're currently at. And if you look, this is just looking at the root mean square errors in the high-res system of this change from 96-hour forecast in the top left to 216-hour forecast in the bottom right. So latitude on the x-axis, pressure again on the y-axis. And the blue and green colours are where we're getting an improvement. So through most of the stratosphere, you see we get a very significant improvement here. There's a slight degradation at the very top of the model where our initial bias is in the different sense. That pulls us the other way. But through the bulk of the stratosphere, we get a very significant improvement from this change. Moving from the stratosphere right down to the surface, a very long-standing issue in the IFS has been in tropical cyclones, the relationship between intensity as measured by central pressure and maximum wind that the model gets. We've long struggled, even if we've got the central pressure right, to have winds high enough in a tropical cyclone. And we're looking at for a long time we've been trying to find the cause of this. Is it numerical, or where's it coming from? But then it turned out that there's experimental evidence that supports this change, that there are issues with the drag over waves in very, very, very high wind conditions. So the plot on the left is the drag coefficient, so the relationship between surface stress and wind that we have as a function of wind speed in the current operational system. And you can see how the drag coefficient, there's a scatter plot here, but the crosses in the middle show the mean of it as a function of wind speed. You can see how the drag coefficient increases with wind speed and then just begins to turn off in the extremely disturbed seas when you're over 45 meters per second, 10-meter winds. the experimental evidence suggested that fall off should occur sooner and sharper. So we've changed the formulation of the drag coefficient in the wave model, and we've moved to this picture on the right, which is completely unchanged for winds less than 30 meters per second. So it doesn't make any difference at all over most of the ocean. But in tropical cyclones, in the windiest areas, we end up with a bit less drag. And if we look at the result of that, to the left, these are the sort of plots I was alluding to before. So we have central pressure on the y-axis against maximum 10-meter wind speed on the x-axis. The plot on the left is for the current operational system, 46R1. And the pink circles and the dotted line are observations from a number of recent tropical cyclones. Yeah, and as expected, as the central pressure goes down, the maximum wind goes up. But if you look at what the model's doing, which is the coloured squares and the dashed line, it's qualitatively doing the right thing, because see, as the pressure goes down, the wind isn't increasing as fast. If you look at the right panel, this is where we go to for cycle 47R1, and you can see the whole model distribution, particularly at high wind speeds, has shifted a bit to the right. The problem's not completely solved, but we're getting, for the same central pressure, higher near-surface winds. Then on the radiation side, there's been a couple of changes to greenhouse gases and incoming solar radiation from the sun, just to make sure we're up to date with the most up-to-date values. But then we've also made changes to the albedo. So two changes here. One is representing the dependence of the direct solar beam on zenith angle. At the moment, we have an albedo for direct radiation, but independent of angle, and a different albedo for diffuse radiation. Here we're swapping to using 6 different albedos, representing the fact that the albedo is different for more glancing angles than for vertical radiation. The other change, and actually the bit which has a bigger impact, is changing the wavelength dependence of the albedo. It's specifically in where visible meets infrared, and in that sort of range of wave numbers. And the change that we've made, again justified by observational data, tends to slightly darken the land surface. You get brighter over snow and sea ice, but over vegetation you get darker, so you get a slight warming of the land. So if you look at the change to the temperature bias in the top left plot, you can see we're tending to get a warming, particularly over Europe and North Africa, and that reduces the root mean square error. The plots on the right confirm that. If you look at 0 UTC, the left-hand plots B and E, you get no impact, which is intuitively what you'd expect. We're changing the solar albedo. Doesn't make any difference at 0 UTC. At 12 UTC, you see that the warming we're getting is beneficial. So I think that's reassuring, observationally justified changes, and the forecasts get more accurate as a result. Now, and I think the last aspect on the model, and this one is a purely diagnostic change rather than a change to the model as it evolves forwards, but we've had, really for computational reasons, a quite simple calculation of convective inhibition, which is an important diagnostic used by some forecasters. We've now revised the calculation in this diagnostic to use virtual potential temperature instead of equivalent potential temperature. So really changing to what we'd like to do, but we found the computational time to do it. And that tends to give a considerable reduction in average SIN values. And I think that we hope and expect will be well received by forecasters, because the values were excessive with the diagnostic we have at the moment. I'm not going to show that many scores. There will be later separate webinars going into the scores in more detail, but just to give you a flavour of what this cycle does in the next few slides. So these are desperately busy slides, so I'm not going to go through the detail of all of them, but just to roughly orient you, these are scorecards for our medium range ensemble. The left half of this slide is verification against analysis. The right half is verification against observations. In each of the halves, we have scores for the Northern Hemisphere, then the southern hemisphere, then the tropics in the vertical columns. And going across the way, we have geopotential height, mean sea level pressure, temperature, winds, moisture, 2-meter temperature. And then the 10 symbols are days 1 to 10 in the forecast, and blue are positive changes and red are degradations. So a lot more blues than reds, which is what we'd hope for. I think notably we tend to have improvements in geopotential height. Stratosphere is very systematically improved. 2-meter temperature and dew point are improved. Against observations, it's fairly neutral in the tropics, with the one exception of there is a slight degradation to 250 hectopascal temperature. Against analysis, the picture looks redder in the tropics, but that's this verification against analysis artifact that I was talking about earlier. So I think overall a very positive cycle, and high res, same against analysis and observations, qualitatively a similar picture. Just to finish with a few tropical cyclone statistics. So here we've lumped across all basins to try and get a large enough sample. So on track, the cycle is neutral, at least average across all basins. There's no statistically significant difference in the forecast track accuracy. If we look at tropical cyclone intensity as measured by central pressure, there is a slight degradation. We're at 47 R1, our intensity, we tend to have not quite so deep tropical cyclones. So that is a slight degradation. But if we look at the winds, we actually have an improvement in the winds. So the top left plot, for example, is the mean wind error left to right as a function of forecast range. And so we'd like to be 0, the horizontal black line. Red is where we currently are, and blue is where this cycle takes us to. So what's happening there is we have this very small degradation in intensity as measured by central pressure, but that's more than compensated for the fact that it's considerably windier for the same central pressure. So overall, the tropical cyclone winds are improved. I think the last result slide I was going to show is the extended range system. We have a seamless approach, so whenever we implement a new cycle, it goes in the medium range and in the extended range, the monthly system. And we also, although it won't be implemented at the same time, we also look at the impacts on seasonal timescales just to assure ourselves we're doing something which is scientifically correct. But really, this cycle, actually, the impact on the extended range is really pretty neutral. The left panel here is one of our usual scorecards, analogous to the ensemble ones I was showing, but for the medium range, different variables, northern hemisphere, tropics, weeks 1 to 4. And the fact you can't see very many colours on that is indicative there aren't very many statistically significant changes. Perhaps some improvements in 50 hectopascal winds, so stratospheric improvements again, which is consistent maybe with what we'd expect. On the other hand, a slight weakening of the amplitude of the MJO, which is a slight degradation, but overall very little impact on the extended range system. So in terms of next steps, we'll be implementing this cycle on the 30th of June. As you've probably seen on the web page, there are further webinars coming in May. They'll be more focused on the verification, technical access to the data, products, new parameters, and less on the background science that I've been talking on. But I hope they will be of interest to people who tune into those. And so the link here is to the cycle implementation wiki page. So yeah, those interested in this cycle as it develops and moves to operations, please do follow that page to keep in touch. So I'll finish there, and I'm happy to try and take any questions that people fire me through the chat.